Good morning, good afternoon, good evening, whatever the case may be. We are back and better than ever. We're going to talk about the modulus. It's a bit funky, so we let off with a funky tune of sorts. Let's get right down to it, shall we? Giddy up. All right, so vectors have a magnitude and direction, and we can also attribute a magnitude and direction to complex numbers. The magnitude of a complex number is called its modulus, and its direction is called its argument. If you think about that for just a second, it makes perfect sense. This might provide a little bit more clarity. The modulus of the complex number, z equals a plus bi, is the length of the vector, which is the real number, mod z, modulus, mod z equals the square root of a squared plus b squared, because ab is the magnitude of the vector, which is the length. Now, this is the distance from the origin, 0. So modulus and absolute value, really the same concept. And then there's a little bit more connecting it here. I'm not going to go through it. Hopefully it is obvious. Okay, so we're just going to do one of these. Find mod z for z equal to one of these numbers. So let's just do part C. Okay, so mod z would simply be equal to the square root of -3 squared plus -2 squared, which we know is root 13, right? So all three of these clearly are going to have a modulus or mod of root 13. Okay. Now we are going to prove that mod z1 z2 equals mod z1 times mod z2 for all complex numbers z1 and z2. So we are going to let z1 equal a plus bi, and z2 is going to equal c plus di. Okay, so let's see. Let's do z1, z2 first. So that means z1, z2 is going to equal a plus bi times c plus di. And if we expand that, collect all like terms, we're going to end up with AC minus BD plus I times AD plus BC. If you want to pause and work that out to convince yourself, go ahead, but it's just algebra, so you can trust me. Okay, so if this is true, which it is, then mod Z1, Z2 is equal to the square root of these guys. Oops, I forgot a thing here, didn't I? I guess I should have used parentheses in there. Why didn't I do that? Well, I got brackets and brackets. It doesn't matter. Okay, so mod z1, z2 is simply going to be, now this is z1, z2. It's going to be the square root of the square of each of the real and imaginary parts here. So AC minus BD squared plus AD plus BC, the quantity squared. And then I think I'm going to skip a couple steps here. Well, no. This would be equal to the square root of a squared c squared minus 2abcd. And if you want to work, I am skipping some things here, plus b squared d squared. That's expanding this thing, right? Plus a squared d squared plus 2abcd and plus b squared c squared. Hopefully you can see where this is headed. Ka-pow, yes? Okay, so then I'm going to have to move up here. Sorry, ran out of room. So this equals square root of a squared times c squared plus d squared A little bit of factoring, algebraic manipulation, b squared times c squared plus d squared. Ooh, now the common factor is c squared plus d squared. So we're left with, that's equal to the square root of a squared plus b squared times c squared plus d, that's a horrible c squared plus d squared. Giddy up, giddy up, giddy up, which is equal to the square, see where we're going? A squared plus b squared times the square root of c squared plus d squared, which is equal to mod z1 times mod z2. In your face. Very simple, very easy. Okay. That leads us to some properties of modulus. Some of them we just proved this one right here, so we could prove all of these similarly. This is from this chapter. This is from a previous chapter, and I've checked these two because we are going to use them to solve a problem. Okay, and I put them right here too. So they want us to find mod z giving this equation. So let's get to it, shall we? So if we square both sides, okay, I'm going to go ahead and square both sides. It's a love story, baby, just say yes. Then I am going to get 25 times mod z minus 1 squared is equal to mod z minus 25 squared. Okay, are we good? Now we are going to use this and rewrite this thusly. 25 times z minus 1 times z minus 1 star, which is the conjugate of z minus 1, is equal to z minus 25 times z minus 25 star. Okay, and all I did is I wrote the mod of z squared using this formula, z times z star. And you might be thinking, wait a second, Mr. B, z equals a plus bi. What's this minus 25? What's this minus 1? Well, the a and the minus 1 could combine to form a constant, so we're just leaving it in this form. Okay, now we're going to use this one. Okay, and what happens from there is 25 times z minus 1 times z star minus 1. All I'm doing is z1 minus z2 star, I'm just moving the star here, okay, equals z1 star minus z2 star, okay, no big whoop there. But what happens here? Well, this is its own, if you can think of the minus 1 as its own complex number, negative 1 plus 0i, then it works out. We already have the star. This is just right in here is minus 0i, so we're okay. So this is z minus 25 times z star minus 25. Okay, and you might think this is trickery or magic, so I did an algebraic proof of both of these, and if you're not convinced, then pause the video and just go through it and you'll see the proof. So pause it here if you want before you continue. All right, I'm going back to continue the manipulation. Now it's just a whole lot of algebra. Okay, so if we expand this and distribute the 25, we end up with 25 z star minus 25z minus 25z star equals zz star minus 25z minus 25z star plus 625. So you can see what's happening here. We are left with 24 z star okay, subtracting here, and then these guys are destroyed, is equal to 600. Okay. Oops, I forgot a plus 25 here on this expansion, which makes sense. -1 times a -1 is 1 times 25. So that's why that's 600. Sorry about that. So then ZZ star would be equal to 25. And ZZ star, again, is equal to mod Z squared. So mod Z squared equals 25. And therefore, mod Z is equal to 5. That is a thing of beauty. So I'm going to stop because I just got a couple small examples left, and I don't want to go too long, give you a little bit of break. Let's check back in with that funky music, shall we? And we'll go on to part 2. I am out!